Hi, in this video I'm going to show an example of how using the GPU Performance Analyzer, which is a tool to identify, visualize, and mitigate performance bottlenecks in GPU generated code. The example that I'm going to use is fog rectification, which is an algorithm to remove fog from an image. And I'm going to put this article showing fog rectification, and also the main article, which has the link for that as well, in the description of this video. And basically, the fog algorithm is an image processing pipeline which have some bottlenecks that we are going to identify through the GPU Performance Analyzer. To open the example, just click on Open Live Script, and that'll take us to the folder where the example is. Now we're at the example, and the first step is to verify that the GPU configuration is correct. For that, we use these commands, and for my case, they're gonna work. But in case that they do not work, the main article is gonna have a couple of links that I'm also gonna include in the description of this video, which is identify the requirements. If, for example, you have to have CUDA installed, I have a version 11.8 that is compatible with Visual Studio 2019 and 2022, which I have installed in my machine. And also there are some requirements of having also the NVIDIA software, including NVIDIA Nightside, which is important for this particular tool. And once you have all of this installed, you have to have some environment variables set, and that's the second link. So you can make sure that if something goes wrong, this is a place that you can look into. For example, the path to the installed software has to be in the path, and you can verify it in the prompting here by typing echo path. We're gonna see it in a moment. I'm going okay, finish, and there was no error, so it's working fine for my machine. And you can see here your path. You can verify that everything is correct, so we're moving on. So in the fog algorithm, we can see a pipeline. There is basically a MATLAB function that takes an input image and returns an output image without the fog. So there's going to be a series of operations, many of them vectorized, and you can see that there's some simple operations like scaling, but this one in convolution might be one of the heaviest one. And also there's IM2 gray, histograms, and others. Okay, so now we're going to analyze this with the GPU Performance Analyzer, and this is the command to run the GPU Performance Analyzer. And to run it is similar to CodeGen. You have to create a configuration. So for the first run, I'm gonna use the DLL embedded coder configuration. And also we have to provide, like in CodeGen command from MATLAB coder, we have to provide the inputs as accelerate so that the types can be inferred from them, because the MATLAB function can have any size, so you can infer the sizes out of that. And we're gonna see, you can see the image is 480 by 640 by 3. And let's take a look at the image, which is basically the image with the fog, and although for this example it doesn't matter much. And then finally you have to specify the name of the algorithm, which is the name of the function. And now we run the command with the inputs, the name of the function, the configuration, and we're going to use 2 iterations for this. Okay, so it's going to take a while to load. As you can see, it takes a while because it's generating GPU code. So the analysis is going to be done in the generated GPU code. Okay, finish generating GPU code, and we get the GPU Performance Analyzer window, and we have various panes. One in the left list all the tasks that we have, including the fog rectification main loop 0, which is one of the most important parts. And also you're gonna see that it includes memory transfer, includes memory allocation and synchronization tasks, and you can filter them by this. For example, if I just want to see the actual algorithm, I just leave the algorithm, and you can see it in here. And you can see from here that it basically highlights the particular task, and we can see that all these kernels belong to that main loop 0. yeah, yeah. So there are other kernels, but at least many of them come from the loop 0. And also you can see the memory transfer from GPU to CPU to GPU and vice versa. We can see a memory allocation, which it basically constitutes a large chunk of the memory, of the execution time, and other events like synchronization when the algorithm is executing on the GPU. So if we want to see the total time, we can select all, and you can see in here that it took 6.2 seconds, and in the GPU it takes a little less. But this is, and when you click here, you get the same information that you get in hovering, but with more details in here. The start time, the end time is the same that we get in here. And also we get a summary of the distribution of execution. As we can see in the GPU, currently we spent 80% idle, which is not good, and only 50% on the kernel. And that could be related to this memory allocation and the allocation, and we're gonna do something about it. And yeah, for the CPU we get the same, we get all this overhead that could be related to this, and you can highlight the different parts. Okay, so let's say that we want to focus on this one, on this particular task in here. Then you get a zoom to it. You get more information, like the execution in the GPU. You're gonna see the grid size, the block size, the number of threads, and you can see the time range where it corresponds, and you can zoom out of there with the scrolling of your mouse, and you can see the distribution that is relative to the zoom that I have in the profiling timeline. Okay, so another good thing that this has is that you can filter tasks by the times. Let's say that I want to find out which tasks take less than half second. The synchronization task, there's one that free memory took half second, but notice that the bottleneck doesn't happen because of this large task, but many small tasks for memory management. Okay, so now we know that the algorithm came from this is one of the main parts of the algorithm, this that has all these kernels that execute in the GPU. I want to find out where they come from. So I go back to the desktop and use the MATLAB Coder report for that. And you have a link after running the GPU Performance Analyzer. So let's click that link and look for that loop 0 in the generated code. So for that we go to the generated GPU code, which is the name of the function .cu, which is CUDA. So this is where the algorithm is. So let's search for loop 0, and you're gonna find a tag for it. So this is the loop, and then we hit on trace code to see where does it belong to the original MATLAB code. And we see that it belongs to a convolution, the function that I suspected that was gonna have an impact on the performance. And that one, as we saw in the GPU Performance Analyzer, it has like various kernels that come from the implementation of that function, which comes packaged with MATLAB. It's not something that comes with the example. Okay, so there's another example. I'm gonna put a link into the description of this video to another video that shows how to modify the kernel to make it more efficient using the GPU Performance Analyzer for the surf algorithm. Okay, so now let's improve the performance by using the memory management tool from the GPU configuration. Okay, let's go down in the example, and we're gonna use a different configuration. We're not gonna use embedded coder, just DLL, and we're gonna enable the memory manager. And let's see the impact of using the memory manager in the example. So we're gonna use the same fork rectification with the same inputs, and the new configuration with 2 iterations, same command. Okay, let's see how it looks now. when we run the GPU performance analyzer command, it's gonna generate GPU code again with the new configuration. Okay, so I finished generating GPU code. So now the total time is 2.5 seconds, which is less than a half that we got last time, and you can see that the memory management is much less. It's concentrated in the middle. There's nothing in the borders, and yeah. So now the GPU utilization time for the kernel is 37%, increased from 15%, and we have idle time of 51% rather than 80. Again, there are things that could be done maybe in the algorithm, and for that again I recommend the serve algorithm video in the link that I'm gonna put in the description of this video. Thank you very much.